Welcome to Analog Integrated Circuits Design class. This is lecture number 7 of Unit 2. In today's class, we will look at the next architecture, which is two-stage op-amp. But before starting with two-stage op-amp, let us quickly see what we have done the other day, yesterday. So we started with the design of folded cascode op-amp, and we saw how we can design it by allocating current first. Later we assign the overdrive voltage, and then with that we obtain the size of the transistors. And to find the size of input transistor, we have obtained the optimum output DC level. And by assuming that if we short the op-amp output to input for a part of operation, maybe for unity gain buffer or any such application, definitely output DC level should be same as input DC level, and that DC I am considering as a minimum input common mode level. And with that I have sized the input transistors as well as the tail current source. Now with that sizing, in step 4 I have just taken only the half circuit, equivalent circuit. So I think from the main circuit, as I mentioned, this node is the line of symmetry point, and that will be at ground. That is how you can see this as the equivalent circuit. From equivalent circuit I have written the voltage gain equation, and I asked you to find or to get the values of all this. So can you quickly tell me the values of gm and r naught, gm of 1 and 2? What is the value of gm of 1 and 2? So no response means no one tried it. So any response for this gm values and r naught values? All right, so I'll assume that no one tried that. That is why I'm not getting response. That is my assumption. I don't know whether it is right or not. So I am giving you the answers, and you can have a cross check when you get time. You can calculate and have a cross check. GM1 and 2, it is 6 milliamps per volt, and GM3 and 4, it is around 3.75 milliamps per volt. Yeah, anyway, I'm not writing the unit of that. It is amps per volt, and I'm writing in only milli. And this is 5 milli. R naught of 1 comma 2 is 13.3 K. 3 comma 4 is 6.66 K, and 5 comma 8 is 13.3 K again. Now if you substitute these values to this gain expression, yes Bhavya, oh that's very good, you got the answer as 415. Yeah, maybe I got little lesser than that. I am getting around 372. I don't know. So Bhavya, you can check whether you got all the values, gm r naught values as same what I have written here. No, yeah, Vaishnavi, 371, 372 you will get, yes. Maybe Bhavya, you can slightly, you can recalculate or not record, because anyway 372 or 415, it is not meeting the specification and we have to do something with that. Okay. So let me write the values here. So it is 6 milli into GM5 R05 R07. If you look at the combination, you will get this as 888 kilo. You can verify this in parallel to GM3 R03 is around 3.75 milli into 6.66 K. So that milli and kilo will get cancelled. And R01 parallel to R09. I'm just writing the values directly here. R01 is 13.3 K and R09. So I think I didn't write what is R09, which is the ninth transistor. Yeah, so that should have a lesser resistance because that is carrying a current of 1.5 milliamps. So R0 9 and 10, the value is around 3.33 K. So this is 3.33 K. So this is how you have the gain expression. All right. So if I continue and if I write this further, if I simplify this further, this is 888K in parallel to 66K. And this will give you a value of 372. All right. So why I have written in this form? Anyway, we know that the gain is not meeting the spec. Right, 372 is very less, and what I am expecting is around 2000. So anyway, we know that we have to do something to improve the gain. But what I can do here, so in order to see or in order to check where is the improvement required, if you look at this expression itself, we can say that 888K is a huge resistance, but that is coming in parallel to 66K, which is very less. This is less. Now this less, the factor of the low value resistance here is basically coming from this low value. 3.33K looks like a very small value. That is why 3.33K in parallel to 13.3 is giving you a smaller value that is affecting the overall gain of the circuit. That's okay, Bhavya. GM5 was wrong for you. All right, that is 5 milli maybe, but anyway, it is 472, right? Sorry, 415, which is very close to 372. But you should get the right value such that you can check where you need improvement. Yeah. So Vaishnavi, I think you have written the answer for R0 9 and 10. I just saw it. Thank you for that. Okay, now what we need to do is, since we understood that output resistance or the gain is less, and when we traced back, that is because of the factor of this, or basically the gain is getting affected because of this factor. And in that, since the resistance R0 and R9 are getting parallel, and that R0 9 is small because of, since it is carrying a larger current, that is affecting the gain a lot. So what we will do for that is, yeah, so what we'll do here is, we will, yeah, so what is the automatic solution, how we can improve the output resistance? As we have done for the in the other day, the only option is to increase W by L of 9 and 10, because I cannot increase only length, because, or so what I'm trying to do here is, if I want to improve R0, so I'll write it here, R0 I can improve by 1 by lambda ID, but I cannot touch ID, because if I touch ID, you will have, I cannot reduce ID because I need to recalculate everything. So the first thing, or the very basic thing what I can do is, I can try changing or getting a different lambda, and we know that lambda is proportional to 1 by L. So as L increases, your lambda will actually reduce, and if lambda reduces, R0 will increase. That is the basic thing what I'm trying to do. And so W by L of 9 and 10. So in the previous calculation, I obtained that W by L of 9 and 10 is equal to 400. Or if I write, looking at the width and length separately, this can also be written as 200 micrometer divided by 500 nanometer, which is equal to 0.5 micrometer. This is the W by L ratio of 9 and 10. So as a first step, what we will do is, we'll multiply both with a factor of 2, such that W by L remains same, but your width becomes 400 micrometer and length becomes 1 micrometer. So what is the difference? We have increased the length of 9 and 10 by a factor of 2. That means, that implies that lambda reduced by a factor of 2. Lambda is reduced by a factor of 2. So that means I need to recalculate the resistance R0 of 9 and 10 as 1 divided by. So previously your lambda value was 0.2, since it was a PMOS device. Now when it is reduced by a factor of 2, so what it happens is, it will become 0.1. So it is 0.1 into the current through that is 1.5 milliamps. So what is the new resistance value? Can anyone of you tell me what is the new resistance value? It is just basically doubling of the previous resistance. What is the resistance, new resistance value R0, 9 and 10? Are you guys listening? Can I get some response? Yes, it is 6.66K. That is the value. Now let me check. The value what I have is 3.33. Now it is 6.66 parallel to 13.3. We can expect a slight increase in that, but it will not affect, or I don't think it will. That is the only thing what we need. So one of you, can you tell me what is the new gain value if you are substituting R0 9 as 6.66 in this? Will we get the required specification, gain specification? So with the new value of R0, I am checking the gain. So I'm checking the new gain X value. So one of you check and let me know what is the new gain value. Yeah, so I don't think it will meet the specification. So what I can do is I can, if you're getting the answer, please do let me know. Otherwise, yeah, I'm just leaving it. So what you need to do is you need to check for this and improve the resistance, and thereby you can bring up the gain value. So your gain value should be somewhat close to 2000. It should not be so less than 1000. It should be close to 2000. And if that is not happening in 1 or 2 times, you can actually increase the length at least 3 to 4 times than the minimum length. You can keep on increasing that. Maybe you can try for 4 times the length and see at what value of length you are getting the exact answer, or slightly close to uh, 2000, right? So that I'm leaving for you as a homework. You can check and see the gain specification is met. All right, so uh, the only one technique what I'm telling now to improve gain is to look at the current source transistor, and since the current is more and the length is kept as 500 nanometer, that is giving a low resistance, and that is what is impacting the voltage gain expression. So you have to improve that, and that is possible by doubling or thrice or quadrupling the width and length together. That I'm leaving for you as an exercise, and see whether you are able to get the appropriate or the required gain from that. All right, so with that we are moving to the next architecture, which is your two-stage op-amp. All right, so the folded cascode op-amp and the telescopic op-amp, what we discussed before that, those two op-amps are single stage op-amps, and um, both architectures has its own advantages and disadvantages. Now, um, two-stage op-amp is a specific architecture. So let me discuss about two-stage op-amp now. So two-stage op-amp. So if you look at one of the limitation of single stage op-amp is one of limitation of single stage op-amp. Definitely in telescopic we have seen that, and in folded cascode it is slightly better than that. We didn't discuss that in detail. We'll do that with the help of a numerical. But if you generally look at the single stage op-amp, we will focus on getting a larger gain, and we will also focus on getting a larger swing. And then when we try to get both swing and gain together, at some point we will fail, or the architectures will not be able to provide higher gain and higher swing together. So that is one of the main limitation of a single stage op-amp. And if when we try to have a larger gain, what happens is we will try to keep lot many transistors in cascode, and which will in turn reduce the output voltage swing. So swing limitation is one of the limitation of a single stage op-amp. So the idea of a two-stage op-amp is to have two different stages dedicated for gain and swing separate. So to keep it simple, I can say in two-stage op-amp there will be two stages. The first stage will be dedicated to have a larger gain. So I'll say this is a high gain stage. And the second stage is dedicated to have a larger swing. So thereby we call this as a two-stage op-amp. And this two-stage op-amp can be a fully differential version, or it can be a single-ended version, right? This is a general block diagram of a two-stage op-amp. So this will give you large gain, high gain, and large swing. Now, are you guys with me? Can I get your response in the chat box? Are you listening what we are doing as two-stage op-amp? The need of two stages, and the how we are using individual stage. The first stage for high gain, and the second stage for high swing or large swing. Yes, thank you for your response. Now we will see what are the choices we have to for the implementation of both high gain as well as large swing stage. So I can say that this is stage 1 and this is stage 2. And what are the options we have for a high gain stage? What are the options as of now? We have three options. One is our regular differential amplifier. Then we have something called as the first architecture what we learned, which is telescopic op-amp. And then we also have this folded cascode op-amp. So these are the three options what we have as the first stage, which can provide a large gain. So it can be differential amplifier, it can be a telescopic op-amp, or it can be a folded cascode op-amp. Now, since the second stage is mainly to have a larger swing, we need a very simple stage in the sense we need a stage with very less number of transistors, but it can contribute to gain. So what will be the gain of the combined gain here? AV, say this is AV1 and this is AV2 in volts per volt. The combined gain will be actually AV1 into AV2. So the first stage is giving you a gain of say 1000, and the second stage giving you a gain of 2. I'm just saying it is gain of 2. So you will actually get a the combined gain of 2000. So but it is not like this. We will give 2 in the first stage and second stage and 1000 in the second stage, because we'll definitely get a larger gain than 2 with a simple common source amplifier also, right? Yeah. So what I was telling is the second stage, since it is meant for a larger swing, we will actually use only less number of transistor. So the generally what we use as the second stage is a simple CS amplifier. A simple CS amplifier will have a gain of GM into R0 parallel R0, and that will be kept at the output stage or the second stage, which can actually give a larger swing. All right, so this is how you choose stage 1 and stage 2 for a two-stage op-amp. All right, so now can I ask you to draw the structure of a two-stage op-amp, like a fully differential two-stage op-amp? Can you guys try? Keep the first stage as a differential amplifier and the second stage as a common source amplifier. Can you guys try to draw the circuit diagram of a two-stage op-amp? And if you guys have done that, can you take a pic of that and post in the WhatsApp group now? The first stage can be a differential amplifier and the second stage can be a common source amplifier. So what you can draw is you can draw a fully differential two-stage op-amp. Fully differential two-stage op-amp. How many of you are trying? Can I get your response in the chat? All right, Bhuvan. Yes. Thank you, Avinash, Bhuvan, Anushka, Yashita, Bharat. Yes. So you can try, and if you're getting a pic, oh, thank you. I think a lot of response. If you're getting the circuit diagram, don't worry. You can just post it. I can tell you whether the circuit diagram is correct or not. Fully differential two-stage op-amp. First stage can be a differential amplifier. Second stage is common source amplifier. Don't worry if you are making a mistake also, that's fine. Whatever you are getting, you can just post it. I'm just waiting for at least one diagram. All right, that's from Bhuvan first. Yes, Bhuvan, yes. Yeah, that diagram, that is right. Mm, yes, the second diagram is also right. Yeah, who is this? Second, Avinash. Okay, all right. Yeah. Yeah, so that's right. So others, those who are trying, you can keep on posting there. I'll look at the circuit diagram. So now I will draw the diagram here. So the very simple way to draw two-stage op-amp is to have a differential amplifier as first stage and a common source amplifier as the second stage. But there is a small difference in the way what you have drawn. So what we generally do is, yeah, this is your differential amplifier. This will, this is the in, these are the input transistors, so we'll keep this. Input is provided like this, vid, and this will be biased. So this is vb, this is m1, this is m2, this is m3, and this is m4. Now the output of this should actually go, and it should bias the next stage, right? The output DC should bias the next stage, and that through that signal actually should go. So if I see the pictures posted in WhatsApp, I think yes, Anushka also has posted. Yes, so the, yeah, Anushka, whatever you have drawn is a single ended. That is fine. What I asked is differential, but it is okay. It's single, but single ended is correct. What you have drawn as single ended is right. All right. Yes, Vaishnavi. Yes, you have written that the output is given to the gate of the first transistor, right? So there is a yeah. So the pictures posted in WhatsApp are slightly different. If you can look at those pictures, you will understand that in the initial pictures, you have given the output of the first stage to the input of the NMOS device. But generally, what we do is we will connect PMOS here, and input from the, or the output of the first stage is given as the input to the PMOS device. I'll tell you why we are doing in this way. And then the second stage, even though it is a CS amplifier, we will use a CS amplifier with the PMOS as the input, and we'll keep load as NMOS device. Similarly, on this side also, this is how we connect. All right, and the final output we'll take from here. So this is this can be called as Vout1 and Vout2. Right. So if you ask me why are we doing in this fashion, do you have any answer for that? What can be the reason we are connecting a PMOS CS amplifier at the output stage? This is M7 and M8. What do you think? What can be the reason? If you ask me, can we give the other way? Can we give the output of the first stage directly to the input of the second stage? Yes, we can do that, but there is a small uh, problem there. When I'll not say it is a problem, because you see here, uh, when I try to connect the output of the first stage to the gate of this NMOS, you see there is a that when I do that shorting, actually I'm connecting the output DC level of first stage to the gate of the first MOSFET, right? Or the gate of the MOSFET in the second stage. So this output DC level is actually at a higher value. So what will be this output DC? This output DC will be equal to VDD minus 1 overdrive, right? So such a large DC volt, when I say large, it is not like tens or hundreds of volt, but when we compare this with the low voltage supply, the voltage coming here is large, and that large voltage we are connecting to the gate of the M6, right? So it can actually affect the output swing of the second stage. So it is better to have the output of the first stage connected to the PMOS, uh, so that we are connecting a voltage, we are connecting the DC level of the first stage to the gate of the second stage, and we have one more transistor down here, right? So, and this transistor, what we'll do here is we will actually connect all these gates together, and we will actually give a bias voltage. This is what the common practice to have the circuit in its proper way. This is how we have to connect it. So this will definitely in turn affect the output swing as well, because the output stage of the output DC of the first stage will definitely have a sufficient voltage, and that can actually turn on, or that can keep the M5 and M7 transistor, PMOS transistor, in saturation, and the load devices M6 and M8 can be biased with the same bias voltage of the tail current source of the first stage. So this is how we need to go for a fully differential two-stage op-amp. But if you ask me, whatever you have drawn the other way is wrong, it is not wrong. That is also a cascade of two-stage, the cascade of a differential amplifier and a CS amplifier. But this will actually give you a larger output swing. All right. So now if I look at the gain expression, gain can be written as AV1 into AV2. So what is AV1? Voltage gain of the first stage. The first stage will have a voltage gain of GM of 1 comma 2 into R naught of 1 comma 2 parallel to R naught of 3 comma 4. This is the gain of first stage. If we look at gain of second stage, that is equal to GM5 into, or GM5 or 7 into R naught 5 comma 7 parallel to R naught 6 comma 8. This is the voltage gain of the second stage. So the combined voltage gain will be AV1 into AV2, which will be definitely quite a large value. Now looking at output swing can be directly written as VDD minus 2 overdrive. One is overdrive of 5 if I'm looking only at the right hand side, and another one is overdrive of 6. So this will be the output swing. And if I look for differential output swing, the differential output swing will be twice of this value. So 2 times of VDD minus VOD 5 minus VOD 6. This is differential output swing, right? Now so what we are using as the first stage in this circuit diagram, what you're seeing is a simple differential amplifier. Depending on our requirement, you can actually extend the initial or you can make the first stage as a telescopic op-amp, or the first stage as a folded cascode op-amp, depending on how much gain we need. That is in general what we do, right?
So, sir, I have a doubt.
Yes.
So when we were doing this cascade kind of structure in like single stage amplifier, we discussed a limitation as like which said that there is a limitation in the input voltage range for the cascade stage.
I didn't get. There is a limitation in the input.
Input for the cascade stage, like for M6 and M7, there will be a limited input limit swing limitation, right?
M6 and M7.
Oh, M5 and M6. Man.
Okay, M5 and M6. Okay.
For that stage, like the gate, when we are giving the signal to the gate of that amplifier, there'll be a limitation in the input swing because.
Okay.
Right? So we had discussed this, I remember, like as a disadvantage of. Does that exist
I
here
didn't
also?
get that, Bhuvan. No, Bhuvan, I didn't get the question actually. M5 and M6 transistors are there. You are asking there is a limit. Oh, you are asking about like shorting of output to input. Is that the issue you are
Yeah,
asking?
yes, sir. But then it will
Oh,
limit
all
the.
right. So in the telescope.
Yeah.
Oh, okay, okay. Your question is, can we actually do the shorting? Can we do this? Is what you are asking?
No, sir. I meant like since we have shorted the output of the differential amplifier to the next like single stage amplifier.
Hmm.
Input of will there be a limitation in the input range for the single stage amplifier?
Uh, okay, you are asking that will the signal swing here? Will there be a
Yeah, yes, sir.
limitation on the?
Yeah.
All right. So when we, I didn't get exactly what you're asking as limitation, because you're asking how much, what can be the largest signal swing which can be allowed at the gate of M5. Is that your question?
Yes, sir. So
Okay. So if your question is that, this node can definitely have the largest swing, which this entire differential amplifier will provide. It can have that swing. Now, again, when you say that there is a swing here, it is not in terms of volts, right? It is in terms of millivolt. So most of the time, it is in terms of millivolt. So the signal swing at the input of M5 is definitely limited. How it, if you ask me how it is limited, it is limited by the operating region of M5. So M5 should not go out of the saturation region. That is the only condition what we can say here.
yes, sir.
Yeah,
Okay.
so M5 should not move out of the saturation region. So within saturation region, what can be the maximum swing that is allowable? The allowable swing is in such a way that M5 should not move out of the saturation region. So
Yeah.
saturation is the limit of the signal at the input of M5.
Yes, sir.
All right. Yeah, that's a good question, Bhuvan. So actually, we will take up a design of two-stage op-amp, and there, I think we can discuss this more. So how much can be the swing coming at the input stage? Will it affect the saturation region or not? We will look at one problem in detail. Maybe I think that will give you a little more clarity on that.
Yes, sir.
Yeah. So quickly moving on, if I'm asking you to draw the single-ended version of this, uh, how we will do is I'm just taking this figure as it is, and to have a single-ended version, we can make small changes in the circuit. The change can be I'll delete one side because it is anyway single-ended. So this side I'm deleting, and one small changes I'm making in red. So I need to connect in this form. So this change I need to do, and then output will be connected to this point, and the rest of the things remain same. So this will be the single-ended version. So only a thing is you have to actually establish the current mirror connection here, and then the rest will remain same. This is single-ended two-stage op-amp. All right. Now, like one question I'll give you as homework, and with that I'll wind it. Next day we'll continue with the design of two-stage op-amp. So try to draw a two-stage op-amp, which is fully differential, by keeping first stage as telescopic. So you can have the first stage which is telescopic, and the second stage can be a common source amplifier. Second stage can be a common source amplifier. So you can try out this question, and in next class we will do a design of two-stage op-amp, and then we will have one more architecture called as one more technique called as gain boosting, and with that we'll wind up this unit. All right. So if you have any further questions, you can ask now. I can take up questions if you have any doubts or if you want more clarity on any of this. Thank you so much for joining. Please be online.